Okay, good morning again. Today we will talk about the liquid chromatography mass selective detector, and after that about gas chromatography. We talked previously already about the different kinds of detectors in HPLC, or the classical detectors. That means UV detectors, which are most common, the related fluorescence detector, which also detects light, but fluorescent light, not absorbed light, RI or refractive index detector, the ECD, and different electrochemical detectors. Now, the MSD is a little bit different because it's not using just one property and measures this property, but it is more like a second instrument. MSD, or also called mass selective detector, is quite sensitive and basically universal. That means you can basically measure everything. The special thing about the MSD is that you can resolve multiple compounds in a single peak. That means you have a chromatography and you separate things. And normally you want that at the same time there is only one compound coming out. In the MSD you don't care so much. You can even do a chromatographic analysis if you have at the same time more than one thing coming out. And why is that? Because the MSD can give you structure information. So a molecule comes out, you can get an idea about the structure of the molecule coming out. And how? We will go over that in a second. The MSD has a few challenges, and that is that you need ions. You need free-flowing ions in gas. So you have a liquid, your mobile phase. Inside the mobile phase are molecules, and these molecules have to become ions in a gas phase. And that is not very easy. For that we use normally electron spray ionization. The electron spray ionization works in a way that you have your mobile phase with the analyte, good morning, coming in a small capillary. This end of the capillary has a high voltage potential. That means it is connected to a different side, to an electrode with a very high electric difference, potential difference, voltage difference. This makes the molecules inside here charged, but actually not really the molecules, they are free electrons. So what is happening here is that we press a liquid out of a very small, very highly charged filament, we get a Taylor cone. This is a phenomenon where liquid comes out, and because of the high charge it becomes very thin. So it comes out and forms this kind of shape, and then makes very small drops. So here is basically a vacuum, no air. So these small drops, they have these electron charges on the surface. Over time, within seconds, the solvent here, the mobile phase, is evaporating. But the charges cannot evaporate. The electrons cannot just go out, or actually in this case it's lack of electrons. They don't go out. They stay. So the drop is getting smaller and smaller and smaller. Our analyte molecule is also staying there, cannot easily evaporate. So the drop is getting smaller and smaller and smaller. It has the same number of charges. So first, let's say 10 charges, big, gets smaller, gets smaller, gets smaller, still 10 charges, gets smaller, gets smaller, gets smaller, still 10 charges, until it is very small and still has the same number of charges. What happens if you have a plus or minus charge very close together? If you have minus and minus here, or if you have minus and minus here, what's the difference? Repulsion, right? Good morning. We start at 9, by the way. So we get a smaller and smaller droplet with more concentrated charges until they are so concentrated that the droplet breaks. And we get smaller droplets, but many. And then these smaller droplets do the same thing again. Stuff is evaporating, they get smaller and smaller and smaller and smaller and smaller until many charges, and they explode again. This one continues until in the end we have only single molecules left with a single charge on them. So basically we took liquid with molecules inside, over this process produced molecule ions. And these molecule ions then go to the MSD. So this is the ESI, the electron spray ionization. Now, what do we do with these ions? These ions are in a low vacuum. What means vacuum?
No air.
No air? Low pressure because no air, no gases, nothing. But inside there, our mobile phase is evaporating, right? So there is not nothing, there is something. So we have an area where our ions are produced, and in this area there are quite a few molecules. We try to make vacuum here, but still we are evaporating our mobile phase. So in this area there are still many gas ions. It's not good vacuum. But later in our instrument we need good vacuum, also called hard vacuum. So somehow we have to separate the area with not so good vacuum from good vacuum. How could you do that? You have one box with good vacuum and one box with bad vacuum. You can just keep them separate, right? Very easy. No air, little bit air. But now we want that our ions can go from the one box into the other box. How? How can we make only our ions go from here to here and not the air? But how can we stop the guys without a charge from going? Not so easy, actually. The charge itself is not really helpful. If we could give all the water, for example, a negative charge and then make a minus barrier, yeah, could work. But as soon as there's anything neutral, the barrier would not work. So it's quite tricky, actually. So what we are doing is we have an interface with a kinetic barrier. What is kinetic? Something movement or energy related. Normally movement energy related. So what we have here is, we have on this side our ions and gas. And we have a very small hole. We take a gas, for example, nitrogen, and we pump it very strongly this direction. Oh, actually here. We pump it very strong direction, and here is a small angle. So if this gas comes here, it hits this angle and moves this way. Gas goes this way. Any molecule here moving this way is hit by the nitrogen molecules and pushed away. Exactly in the middle, it is pretty small speed because the two hit and go outside. So exactly in the middle is not so strong movement. So exactly through the middle, it's a little bit easier. Anything slightly on the side is easily diverted. And another thing is, our ions from the electron spray ionization are faster. All this solvent, all these molecules go a little bit randomly. They move around. The ions from the ESI are moving more straight and faster actually. So by pumping here that gas, we create here some kind of kinetic barrier for the randomly moving molecules. So we can separate the high vacuum and low vacuum area. So how can we make the ions go faster? Yeah, I think this picture is okay. We have the accelerator plates. We said that our ions are positive charged, right? How can you make a positive ion go fast? Right. So you have an ion, positive. Here you put something negative. And then it starts moving, right? But if you have a plate here and a molecule here, it will go this way. And it will hit, right? Is that good? If our ion hits something, we cannot do anything later with it anymore. We just want to accelerate it. We want to make it faster. But we want that it continually moves. So what we have here actually is an acceleration plate with a hole in the middle. Actually, this is a picture from a double octopole, forget it. But basically here are accelerator plates. Not the best picture for that, but yeah. So our ions are moved forward by electrically charged plates. And then they move at a relatively high speed. Normally we have at least 3 plates after each other, all plates with a hole in the middle. Let me draw that a little bit differently. So we start with our ion source. Here are now some of the molecules charged. Then we have our interface. And then we have our plates which are negative charged. You know, my art is amazing, I know. Thank you very much. So all these positive charged ions move now through the middle very fast. Okay? There are also many ions which hit here or some hit here. They're gone. They lose their kinetic energy if they hit here and they go out. Same here, goes out. So what we get here is actually ions moving very fast in one direction. The important thing is that this speed is relative to the charge. So if you have, let's say, a proton with proton is 1 time charged, it moves at a certain speed, always same, because these ones have the same potential always. It does not change. So all of these ions move basically at the same speed. Good morning. We start at 9. After that, after we accelerate our ions, we somehow want to separate the ions. We have different ions. Normally, when we have our molecules get ionized. What happens if you take, let's say, aspirin, ASS, acetylsalicylic acid, and you put 1 charge on it? Any idea? You remember aspirin, right? ASS, acetylsalicylic acid. What happens if you put 1 plus charge on it? Yes? It becomes unstable. In the case of 1 plus charge, maybe it breaks up a little bit. If you have 1,000 molecules and every one of them gets 1 plus charge, do everybody break up? No? Yes? No? How many? Some. Depends on the molecule. If we have a very big molecule with weak bonds and there's 1 charge, maybe 90% break. If we have a smaller molecule, stronger, maybe only 5% break. Do they all break up in the same way? In the case of aspirin, let's say we have it protonated and deprotonated. So the 1 proton is on, 1 proton is off. Already 2 different things. There can be also the proton from the other location. So we have already 3 different forms. Maybe one of the double bonds break. 1 more form. There are many different possible ways how a molecule can break. Some breaking is more common, some breaking is more difficult. That's what we call fragments. So when a molecule goes through this process and acquires a charge, they can fragment, they can break down. And now comes the interesting part. These fragments, the different sized pieces of the molecule, have a different weight. Still, all of them have 1 charge. Everybody has one electron missing, but they are different big. And we have now metal sticks. These metal sticks we can charge. So you can make this one positive or negative. If we have a small molecule with one negative charge and a big molecule with one negative charge, and they are moving along here, and we charge this stick, what do you think happens to the two different charged molecules or charged fragments? You have a negative space, you have a small positive charged and a big positive charged fragment. Will they move the same way or differently? Negative. Big positive thing. Small positive thing. Do they move same or different?
Different.
How? How different? No? What forces are there? You know from organic chemistry. You took that class, I know. If you have two opposite charges, what forces are between them?
Opposite charge.
Yeah, what forces are between them? No! Van der Waals were induced dipoles. Coulomb forces, right? Coulomb forces, C-O-U-L-M-B, Coulomb forces. That was the force between one opposite charge. So 1 Coulomb is the force between 1 plus and 1 minus charge. Quite small charge, quite small force. So a Coulomb. So if you have 1 plus charge and 1 minus charge, the force between this is 1 Coulomb. Depends on the distance. Depends on the distance between these two. So, but this one is always same. It does not matter we have a thing with 1 positive charge and we have a thing with 1 positive charge. How much force? Well, depends on the distance and the charge. For now, let's say, to make it easier for you, I just say 1. How about these two? Same or different? Same force or different force? Everybody says different? Anybody says same? Why different? One second. No, same charge. 1 charge, 1 charge. Yeah. 1, 1. It's not 2, it's 1. Just the size is different. So same or different?
Different because of having different size.
How is the force involved with the size? The force is some factor for the permeability of that media times the charge difference. I forgot the formula sign for that. I just now call it c, times the length times a constant, c1. I forgot the formula signs, but that's basically it. So if it's same media here, vacuum, this one doesn't matter. If it's the same, it's one electron difference, that's same. If it's the distance is same, it's same. All of these factors are same. So it should be same, right? There is one charge, there's one charge. Same distance, same distance. The size of this one does not affect the force. Okay? So, we have the same force between these two. So, do they move same or differently? Okay. Who says they move same? Who says they move differently? Why?
Because of different size.
Yes, this time yes. If you have a big car and a small car and you use the same power, which car accelerates faster? Yes, of course. If the force is same, but the mass is different, the speed is different. S is the acceleration. So, what happens here is that we have different ions coming in here. And we have charged rods. Different sized molecules, or fragments actually, move differently fast towards the different rods. And now the tricky part. We start alternating the polarization. What does that mean? That means we have here our positive charged ions and we make this one negative. Then the ions will move to here. Then we are changing. We make this one positive and this one negative. Then the ions will try to go there. Then we are changing again. We make this one positive and this one negative. The ions will try to go here while they are moving through here. So in the end, we get a spiral path, like a helix. Here's something, here's something, here's something, here's something. Goes in. Oh, I have to go here. Oh, no, wait, I have to go here. Oh, wait, I have to go here. Here, 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 here. Until we get a spiral path. If the fragment is too big, it's slow moving. It tries to go here, but then the polarity changed already. It tries to go here, but changed already. It tries to go here, but it changed already. It has to be the right size to get into this path. If it's too big, it cannot follow. And sooner or later, it will hit outside. Same if it's too small. Top here, bang, hit, finished. Losing all the speed, hitting the metal, now goes out. By changing the speed, how these ones are changed, we can say that only one size of fragment can pass. So this is actually our mass selection. Different size of fragment coming in, only the fragment fitting that changing speed, that frequency, can pass through. If we have two large molecules, they may go out. If we have two small ones, they also may go out. Only the perfectly size fitting that frequency, how we are changing the polarity, can pass through there. This system we call a quadrupole. What means quadru? 4 and pole, something charged, right? So it is a quadrupole with 4 charged rods. There are also octupoles, but don't worry about that. So we have a method of selecting only a specific fragment size. And now we somehow, important? No, later. Forget about that one for now. Now we have to detect them. We separated them, but we can't see them yet. So how do we see them? Not so difficult actually. This is a pretty old detection method. We have dynodes. Dynodes are round shapes coated with an electron reactive material. What does that mean? Have you ever seen that? Have you ever seen electron reactive material? Ever? Sounds fancy, right? Have you seen a TV? I guess yes, right? The old TVs, the CRTs. Why is light coming out? But why? They're electrons, right? They are charged particles moving at a high speed, hitting a polarized phosphor layer, or some kind of phosphor. And then that one produces photons. Quite similar here. We have a charged material. If an ion is hitting this material, electrons come out. Because of this shape, if something goes in here, all the electrons shooting out come into this direction. Every electron going to here again produces more electrons. And then again produces more electrons. And again produces more electrons. Produces more. So we have a cascade out of one ion producing many electrons. And this is a detector. We easily can get something like a ratio of 1 to 1 million. 1 ion in, 1 million electrons out. Okay, what do we do with the electrons? Can you see electrons? Still difficult, right? But how can we detect electrons? How can we detect electrons? Electrons are charges. So how can we detect them? Nah, come on, not so difficult. Metal plate. Finished. Electrons, metal plate, absorbed, cable, computer. Electrons hitting that metal plate produces a charge. A charge produces a current. Very simple. So as soon as we have the electrons, it becomes easy. Just a metal plate and a cable and finished. So from the beginning, we have molecules inside a liquid. we produce ions. These ions may break into smaller ions. They are put into a hard vacuum, very strong vacuum. No other ions anymore. They move through a system of quadrupoles or octopoles or other things to separate the fragments based on their size. All of them have one charge and we separate by their size. So often we also say by the m to z ratio, mass to charge ratio. Okay? Everybody has one charge, so basically we separate by their mass. And after that, the ions reach a detector where we multiply the ion or fragment ion into many, many electrons. And these electrons we then can use for any stuff in the computer. Two more things. We can do special things. We can do more collisions. We can have inside the detector another chamber where our molecules hit other molecules. And then they make smaller parts. And based on what kind of smaller parts they make, we can get a better idea what kind of molecule it is. This one, forget it, not so important for you. Just information. But one thing you have to understand, and that is, why do we have vacuum? All the time I said vacuum, 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 vacuum. Why? We have this thing. Why do you think we need vacuum?
Not to consider mass.
He started first. Somewhere there I heard something. No?
For not considering mass.
We consider mass. Vacuum doesn't reduce mass. Okay. Yes, no obstacles. If here are other molecules and I try to go through and I hit the other molecule, I change this direction. So this is what we call the mean free path length. How long can a molecule go before it hits other molecule? So in air, it's quite short. Molecule moving, dang, other, dang, other. But here, these ions have to go through without hitting anything. Otherwise, nothing happens. So we need no gas in here. Otherwise, the ions cannot go through. Very important, because we need a long free path for the ions. One thing which I do officially not have in here, but which I want to talk about anyway, is how to do vacuum pumping. How can you make a vacuum? Ideas? How? How can you produce a vacuum? Okay, how does a vacuum pump work? How does a vacuum pump work? What do you think? Don't have to check, you can think.
Engine.
Okay, you need a motor. What does the motor do?
Absorbing gas.
A motor absorbing gas.
Not absorbing.
Ideas?
Suction.
How?
differences.
Okay, how? Gets annoying, doesn't it? No, but how? Have you ever used a pump?
Yes.
Okay, how does it work?
Push out.
So you are describing a piston pump, right? A bicycle pump, for example. Same as in a HPLC. You have a tube and a plunger or piston, and you push down, and the air is moved. Okay. Can you make vacuum with it? Why not? Why not? So a piston pump for making vacuum, does it work?
No.
Why not?
You can push and
No, you can pull, right? You connect it, you pull. But when you pull inside here, why should the air go here? I have the big, let's say I want to make vacuum in here, and I have the piston pump. Pull. Why should the air out of here go into my pump? Only because here is bigger pressure than here, right? So how far can I do it? If there is only a little bit left, and I make here also, there is no reason for them to move. So I make lower pressure here than here, then they move. But as soon as very little pressure and very little pressure, they have no reason to go. So that doesn't work well. So other ideas. Other ideas. How can you get air out? Bless you. Not a vacuum, overpressure. Wrong answer. So how can you get air out? Any ideas, suggestions? If you want to move a lot air, then making a pressure difference is a good idea. It's simple, right? But as soon as you have little bit air left, it's not easy anymore. So what can you do? In a MSD, we are using two different methods. The one is a so-called turbo pump, and the other one is a gas diffusion pump. A turbo pump and a gas diffusion pump. Let's say you have a tube, and inside the tube you have a propeller. And you know that molecules move randomly, right? If you start spinning this one very fast and a molecule reaches here, and this one is actually slanted, and the molecule reaches here and gets hit by that one, then the molecule gets a speed in this direction, right? Same as a propeller underwater. So molecule moves, gets hit by the propeller, gets accelerated this way. This is a turbo pump, basically a propeller. In reality, it looks different. You have basically many propellers. Very small distance and very high speeds. That's number one. This one is still for low vacuum. If there are very few molecules, it's very inefficient. As soon as there's very few molecules, you do something differently. Oops. We have a gas diffusion pump. The picture's just, yeah, forget it. We have oil or something with a very high boiling point, and we make it hot. Then this one produces gas, oil gas. This oil gas we force through a narrow channel, so it gets very fast. And then out of here, so the oil molecules come shooting out of here. And again, they move like this. Any molecule in this area reaching here will be hit by this fast moving oil gas and moved this way. This is very efficient and very strong, especially for very low pressures. If you have here a lot of gas and here a lot of gas, it's pretty useless, doesn't work, not strong enough. But if you have very few molecules on both sides, that means low pressure, then this one is a very good way of moving gas molecules from here to here. But I'm talking about this because there's one important thing about this. What happens if you suddenly shut off the heat? What happens? In here, strong vacuum, out here, small vacuum. What happens?
Is it glass?
No. Inside, strong vacuum, outside, weak vacuum. What happens? Yeah, okay, that means strong vacuum, weak vacuum. What happens? No. If you have here strong vacuum, here low vacuum, what happens? High pressure, low pressure, what happens? Gas is starting to move, right? So we have small vacuum, high vacuum. What happens? Gas moves back in here. High vacuum means very low pressure, no air, little bit air. So gas starts moving the wrong direction. Is that a problem? Why? Okay, yeah, then we have to start again. Okay, no problem, right? What's inside here? Oil gas. So all that oil which we made gas and which we try to make the inside here very empty. And now outside here that oil gas is going back in this way. Do you think that's good? very, very, very bad. Because now this area is actually this area. Now in here we have all that oil and we are fucked. Our wool instrument is contaminated with oil. We can forget it. Clean everything or waste it, buy a new machine. So an oil diffusion pump or gas diffusion pump, never, never, ever switch off the power. If you suddenly switch off the power, there is a chance that the oil gas rushes back in and contaminates your quadrupole area. So super important that MSD is shut down slowly with the right procedure. So first actually here a valve is closed, then this one is cooled down slowly. If you don't do that, you destroy the instrument. So that one, remember, if you don't do it, you can buy this $100,000 instrument again, which is not happy. Okay, so two different types, turbo pumps and gas diffusion pumps. That was the last of the detectors for the liquid chromatography, and now we will talk a little bit about gas chromatography. Gas chromatography is not very different, except that we don't need a pump normally, because we have the gas in a pressurized bottle, so the instruments are quite easier. Our stationary phase is normally a liquid, sometimes a polymer or a liquid polymer. The stationary phase can be inside a tube or a column. These columns can be made out of metal, glass, or different plastics or fused silicas. If there is plastic involved, it has to be plastic with very high temperature stability. We can have columns packed with material same as in the HPLC, or we can also have the columns very long and without anything inside, except maybe thin film. Then we call these capillary columns. In HPLC, we mostly separated by polarity. This is our standard method how we separate things. In gas chromatography, the main separating factor is a boiling point actually. So normally we change retention times by changing the temperature. The temperature then is determining the equilibrium of our analyte between the gas phase and the liquid stationary phase. We have here a few nice abbreviations. That's WCOT, FSWC, and SCOT. The first one is a wall-coated open tubular. The second one is a fused silica wall-coated open tubular, and then the support-coated open tubular. And we have also packed columns. The first three are tubes, open tubes. The one where the wall is coated, that means you have a tube, and inside the wall there is a stationary phase. The second one is the same one, but this tube is made out of silica. And the support open coated tubular is where we have a tube, inside is some material, and that material is coated. And then packed columns is same as you know it from HPLC. You can see here that these columns have different lengths. The fused silica and the non-fused silica are quite long, 10 to 1000 meter. If we have a support material, it's difficult to make them so long. And packed columns are regularly much shorter. Our columns, especially the tubular columns, have a very small inner diameter of under a millimeter. So in HPLC, you saw our columns like 5 millimeter diameter, 7 millimeter diameter. Here they are much thinner. Efficiency is sometimes given in plates per meter. You remember the plates, right? From HPLC or from chromatography theory, the plate from the van Deventer equation is the distance it takes to make an equilibrium. So if we have a plate per meter, that means in 1 meter, how many equilibria can we form? More is better. So in our fused silica and wall-coated open tubular, we have up to 4,000 plates per meter, which is quite good. Then support-coated and packed is a little bit less. The problem, however, with gas chromatography is that we have relatively little amount of stationary phase. What does that mean? Our sample has to move between the mobile phase and the stationary phase. If all stationary phase is bound to analyte, the analyte cannot interact with it. That means if we have only small amount of stationary phase, we can only separate small sample sizes. This is what here is a huge limitation. We can add only very small samples. If we have a packed column, we have so much stationary phase, then we can put much larger amounts of sample. But these tubes have no material inside and it's gas. So there is basically no pressure involved. The gas just flows through it. And therefore, overall, the analysis is quite fast. There's something about inertness. That means actually chemical stability. Our fused silica is very stable. It does not react with anything, it doesn't break, they are very stable. Then traditional columns are not so stable actually. This is a fused silica open wall-coated open tubular column. You have a center face of fused silica. On the outside you have a special plastic, it's polyimide. It's a plastic very temperature stable. On the inside you have magic. This one and this one is easy to make. Well, relatively easy. But on the inside, there the good stuff happens. That means the material, the stationary phase, has to be kinda liquid, should not become gas, should be chemically stable, should have uniform thickness, should be inert. You want so many things at the same time. So somehow you have to make this magically. And the companies are very good at that. Normally these ones are cross-linked polymeric phases. That means, do you know what a polymer is? A polymer, right, you know. You have molecules connected like a linking stuff. And then this one mixed with a liquid and somehow made very chemically stable. fancy stuff. This is the important thing. We call these capillary columns because they are very thin. But all of these, wall-coated open tubular, fused silica wall-coated open tubular, and support open tubular, are all capillary columns, but of course they have a difference in how they are actually made. In HPLC, we said the difficult thing is producing that pressure. We have to press our mobile phase through the stationary phase, and that one is quite difficult. In gas chromatography, we don't have that problem. We have a tube and we have gas. It's very easy to put the gas through the tube. We don't need high pressures. That means we have no pump, and our injector is much simpler. In HPLC, we somehow have to put our sample into the column under high pressure, and that's not so easy. In gas chromatography, we simply have to make our sample into gas. That's all. So what we have is normally a glass tube or silica tube. This one is called the liner. We have a septum, that means a small rubber, and we take our sample with a needle and through the rubber, and we spread it in. Then the sample is in here. This area is quite hot. The sample evaporates and we have gas. And then it goes onto the column. There is one or two special things here. We have gas coming in, gas coming out to the column. But normally we have the possibility to let gas out here. This is called a split flow. Normally the sample goes in here and everything goes down here. If we do a split flow, some of the sample doesn't go down on the column. Why could that be good? Why would we want to put less sample onto the column? Why would we want to put less sample on the column? Why would we want to put less sample on the column? Normally we have the problem that we have too small sample, right? We want more. Here, why won't we put less? Gas, no problem. Pressure, really no problem. Filtering, what do you mean? Just before we talked about the sample size, we said that we have very small amounts of stationary phase. That means we cannot put much sample. Otherwise, we are overloading the stationary phase. We can put only small amount of sample. Is 15 nanogram small or big? Have you ever tried to pipette 15 nanogram? Do you want to try? So it is very difficult sometimes to dilute small enough so that you can inject this kind of amount. Even if you inject like 5 microliter, it can be much more amount than that. So we have here the method of reducing material from the sample without the need to dilute extra. So we can reduce the sample amount by having a split flow removing some of the gas. Other things. We have to evaporate the sample. Gas chromatography, right? But normally our sample is liquid, so we have to boil it. We want it to boil very fast. We inject it, it should be poof, gas. Why? Because if it does it slowly, in the end we get a peak which is very wide. If it takes 5 minutes for the sample to evaporate, in the end we will see the sample over 5 minutes. We want to see it short and high concentration. So we want the sample to evaporate fast. Normally we do something like 20 degrees above the boiling point of the sample. That should be normally okay. So this area is quite hot and you put stuff in it and it should boil directly. This means this area gets dirty. Any impurities might produce charcoal, dirt, and then we have to just waste it and put a new one in. We don't have a sample loop here. If you go back to the six-way valve, this loop is always same volume. If this loop is 20 microliter and I put 25 microliter, the leftover just goes out. If I put 30 microliter, leftover goes out. No matter how much I put, inside that loop is always exactly the same amount. Doesn't matter if I put 20% more, 30% more, 50% more. Inside there, always the same volume. So this one is quite easy to repeat. But here I take a syringe and I push in. How much I have in the syringe determines how much goes onto the column. If I don't put exactly the same amount with the syringe, I will get different amount on the column. So it is very critical that my injection volume, how much I put in, is exactly always the same. That one has to be accurate. And again, we can have this split flow or splitless, no split. There is a possibility of doing a on-column injection. That means we skip all this, we don't put the needle in here and then evaporate and goes down. We put the needle into here. This one, of course, can be only done with super small amounts and is quite difficult, and we start at a lower temperature below the boiling point. So we put it there and then we slowly heat it up. So we get first the low boiling compounds out, then the medium temperature boiling, then the high temperature boiling. Very difficult, not the best way to do it, but if you have very small amounts, it might be worth a try. Or also if your compounds are very sensitive, temperature sensitive, of course. The last injection method I want to talk about is the so-called headspace analysis. The previous stuff was all for liquid samples. But how about if you want to analyze, for example, gases? How can you put a gas? Yes, possible, but not so easy. Often we do it slightly different. we have actually a vial. Downside is a liquid, and this one is closed. The syringe will then not go down here and take sample. It will only go down here and takes a sample. So actually it is taking the gas from over the liquid. Can be quite nice because in here a lot of stuff. In here maybe not so much stuff. For example, if we take your blood and we want to measure the amount of blood in your blood. The amount of alcohol in your blood. There's a lot of different things. It's quite difficult to separate. But if we take the gas above your blood, there's some ethanol inside, right? Ethanol easily evaporates. So we can take from the gas above your blood the gas sample and analyze for alcohol. Much easier, of course, smaller concentration, but much easier to separate. This means we can avoid the extraction. Normally, here we have to do extraction. And you remember extraction from biochemistry? Do you like extraction? Time consuming, costs money, is annoying. So if you can avoid the extraction, that would be good. But measuring gas is not very repeatable. So you have to do it very well to get accurate results, or more better is actually precise results. Often we do this for solvents in pharmaceutical analysis. So everything what easily evaporates, we can analyze with a headspace method. Or as I said, alcohol from blood is also done with that easily. Gas chromatography injectors are quite simple, and otherwise we don't need a pump and we just need a temperature controlled oven. So the basic instrumentation is very simple. We have also a wide variety of detectors, and some of them are quite different than HPLC detectors. We talked already about the mass spectrometer. Actually, mass spectrometer is not perfectly correct. Normally we call it mass selective detector. The difference between the MSD for a GC and the MSD for the LC is only the ionization. If we look back a second, we saw here in the MSD that we have to make the ion out of a liquid. In the gas chromatography, do we need that? Why not? Gas chromatography, yes. So we don't need to make the ions out of a liquid. We have to make the ions out of a gas. How can you make gas into ions? Any idea? Gas is evaporated already. Yes, that's gas. Gas is gaseous, so you don't have to make it into gas. So, how can you make gas into ions? How can you make ions? What is an ion? Something charged, yes. How can you charge molecules? How? Okay, you can give a proton. How can you give a proton? Why should a proton move? You would have to hit the molecule with a proton. Do you know what that is called? Yeah, proton radiation. How is it called? It's called alpha radiation. Do you want to work with alpha radiation?
No.
That's a very good answer. You definitely don't want that. So hitting something with protons is possible, but not the best idea. Other ideas? So not hitting with protons, but hitting with electrons. Okay, that's called beta radiation. Little better. Doesn't kill you so fast. If you don't want to hit it with electrons, what other possibility is there? How can you transfer electrons without actually electron radiation?
Breakdown.
Do you know what an electric field is? You know what an electric field is, right? You have a cable and you put so much electrons through it that there's an electric field around it. And if a molecule goes into that electric field, it takes up electrons. Ta-da, we have our ions. That's it, very simple. If we have a gas, we simply put a wire, or called filament. We put a lot of electrons through it. We make it very hot. And then around there, any molecule passing will get a negative charge. And then the molecule may break down into smaller pieces, fragment. So instead of this complicated method, we simply have a wire which produces electric field around it. So the method for producing the ions is quite easy. Otherwise, the mass spectrometer here is exactly the same. We have the quadrupole, we have different fragments, they have to move through that one, they get accelerated, and in the end we have the detector. Detection limits in the high picogram range, so quite small. And we can basically analyze any sample, which is quite nice. The next one is a so-called flame ionization detector. A flame ionization detector is very nice and sensitive, but funny thing is that it is an amount per second. For the MSD, it's simply the amount. In the flame ionization detector, it's the amount per second. And flame ionization is always used for hydrocarbons. We need carbon in the sample, otherwise it doesn't work. The other one is a thermal conductivity detector, which is very similar to the RI detector from the HPLC. It is also universal, but it's pretty bad. We can measure everything, but we need relatively high concentrations. The ECD, the electron capture detector, works only on halogenated hydrocarbons. So only hydrocarbons with chlorine, fluoride, and so on. But, do you know what that is? What's that F?
Force.
Yes, force gram per second. Good idea. Who studied mathematics well? Mega, kilo, milli, micro. I want to go home. Milli, micro, nano, femto, atto. So this one is femtogram per second. So it's milli is 10 to the power of -3, micro -6, nano -9, pico minus 12, femto minus 15. So that's 10 to the power of minus 15 gram per second. So the ECD is very sensitive. The atomic emission is reported as 1 picogram. I don't think so. But anyway, it's pretty selective. But you can measure only elements. You can't measure molecules. And the chemiluminescence can only measure anything oxidizing. Forget it, not important. Nobody uses it, at least as far as I know. Same with the photoionization, not really useful. Needs some gas sample which are photoactive, forget it. The last two, just skip them. The flame ionization detector is the classical detector for gas chromatography. I think it's even one of the oldest, and it's pretty simple. You have your sample coming as gas, and you take a charged nozzle and you add hydrogen. Then you start burning your sample, and here is the second electrode, and you measure the difference between here and here in current, or actually in voltage. Any carbon in the sample will produce a carbon ion. This carbon ion will hit this electrode and produce a current. So any carbon in here burns, becomes carbon ion produces current in here. So very simple, very fast. You need just hydrogen, not a big deal. But the problem is it's not relative to the amount of sample you have. If you have a sample with a lot carbon, same amount, it produces a stronger signal for the much carbon. Also based on the molecular structure, some molecules produce more carbon ions, some molecules produce less carbon ions. For example, alcohols and amines don't do this well. So the signal is proportional to the total carbon content. And it is not responsive for some carbon compounds, for example, carbon dioxide. Why? Because carbon dioxide doesn't really produce ions inside the hydrogen flame. So it has to be something what can burn and produce the carbon ions. So pretty universal, but it's not great. It's easy and cheap, but yeah, if possible, I prefer different methods. The next one is a TCD, the thermal conductivity detector. In the thermal conductivity detector, we have a Wheatstone bridge. A Wheatstone bridge is a system out of 4 resistors, and between here we measure the signal. We have 2 resistors inside 2 different gas chambers. This gas chamber comes from the column and contains the sample. This one contains the reference flow. Has to be the same flow speed. So for example, 1 liter per minute, 1 liter per minute. Now what happens? We put power through here. Normally, electricity goes this way and this way, same. So we don't see any electrons between here, because left side and right side, same number of electrons. How does it work then? We put a lot of electrons through so that these ones get hot. So still, hot and hot, electrons like to go here and here, same way. Nothing special. Still, left side and right side, same number of electrons. So we can't see anything between here. But now, if here and here is different gas, there is different thermal conductivity. What is thermal conductivity? Please touch your desk. Okay. Now please touch the sink. Touch. Hold, hold, hold. Which one is colder? You're wrong. Of course, same. Air temperature is 18 degrees right now. Why do you think that one should be colder than the desk? Are you stupid? If you touch your paper now, is it warmer or colder? You're wrong. It's same. Why should the paper be suddenly warmer than the air? If you touch the floor, floor is a better example, maybe it's really colder. Why does it feel different? No, no, and no. Yes. Conductivity. What are you feeling? Are you feeling temperature? What are you feeling? If you touch something, do you feel that temperature? What do you feel? How do you feel temperature? You have small sensors, small cells, which give a different electric signal based on their temperature. Yes. So do you feel the temperature? No. You feel the temperature in your skin. So if I touch something, I feel how my skin temperature is changing. So if I touch something where the heat goes out fast, it feels colder. If I touch something, air, where the heat transfer is bad, I don't feel the temperature changing. So you don't feel the heat, you feel the loss of heat in your skin. Big difference, because the metal and the desk has the same temperature, but different heat conductivity. So different gases have different heat conductivity. So we have this wire hot, we have this wire hot, but now different gases. One gas is cooling stronger than the other gas. So we get now a difference in temperature between these two. The gas has the same temperature, but the wire is hot. This gas maybe is cooling stronger, this gas is maybe cooling less. What does it mean? That these two wires have different temperature. And the resistance of a wire depends on the temperature. If you have higher temperature, more or less resistance. Any idea? Normally, if you have a wire more and you increase the temperature, more resistance or less resistance? No, for electricity. If I steal his earphones and I put 10,000 volts through this, okay, and then I make them hot. Is the current going easier or more difficult?
Easy.
Easier, yes. Resistance decreases normally with higher temperature. There are some materials which are other way around, but normally higher temperature, lower resistance. So now we have these two parts, different resistance. Now where do the electrons go? Same or different? Let's say low resistance, high resistance. Electrons, do they still go 50-50? No. How? Do they go to the low resistance or the high resistance? Low resistance. Electrons always go the path of low resistance. So if here is hotter than here, the electrons will suddenly go all this direction. So now, between these two is a difference. Right side and left side, different number of electrons, so we can measure the current between these 2 points. So a thermal conductivity detector has 2 filaments in a Wheatstone bridge design. Gas is flowing over this one and over this one. We heat these 2 filaments, and the thermal conductivity of the gas changes the flow of the electrons, and that one we can see as a signal. If there's any other molecule in the gas, the thermal conductivity changes. Same as the refractive index in HPLC. This is universal. Anything I put into the gas will change the thermal conductivity, mostly because of the density, but why is not so important. So it is universal, but it's not sensitive. It's very difficult to see a difference in that one. One thing which might be interesting is it's non-destructive. The compound does not break. You still can use it for other stuff if you want to. Okay, that's a TCD. And maybe the most fun is the ECD, the electron capture detector. Why is it most fun? Because radioactivity, yay! We have normally a cesium or sometimes nickel radioactive source. That is beta radioactivity. That stuff degrades and produces beta radiation. Do never ever fucking touch that. Okay? Do not disassemble, do not do maintenance, stay away from it if you don't want to die horribly of cancer. So that beta source normally produces electrons. And around here is an anode which is catching these electrons. Very easy. Inside, radioactivity, outside, catching electrons. So you can always see there are some electrons. But if you have electronegative compounds like halogens, which can be ionized, they move here and they are hit by an electron, they take that electron. Then if they catch that electron, the electron is not reaching this area anymore. So you have less current. So super simple. You simply see, are some of the electrons caught by halogen compounds? That's it. I don't know what else to say about it. That's it. You need halogen compounds. Only halogenated hydrocarbons can catch the beta radiation. And too simple. questions? Okay, so again, radioactive beta radiation, normally we see the electrons, hydrocarbon with the halogen group goes, catches the beta radiation, then we see different electrons at the anode. That's all. Super sensitive, but only for halogens. Oh, this one is also interesting because many poisons, pesticides and nerve gases and so on, are halogenated compounds. Fluoride, chloride compounds are normally quite dangerous. And the last detector I'm mentioning is the ultraviolet detector, UV detector, but for gas. Okay. This is a little bit special because it's a vacuum ultraviolet detector. Why do you think vacuum is interesting here? Why is it interesting to have a vacuum ultraviolet detector? And of course it is written down there, so I will hide that. Why do you think a vacuum ultraviolet detector is important? I now can see who reviewed last week's class material because we talked about that. Who can tell me what the UV cutoff is? Okay, you didn't study? UV cutoff? Didn't study? Didn't study? UV cutoff? Ice cream. UV cutoff? 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 Good job, guys. You know that next week is a quiz, right? Every bond absorbs photons. The only question is what wavelengths. They all absorb based on their energy gap between HOMO and LUMO, between the highest molecule orbital and the lowest, highest occupied molecule orbital and lowest unoccupied molecule orbital. That means every bond can theoretically absorb UV light, or light in general. Sigma bonds can, pi bonds can. That is why we have the UV cutoff, why we have wavelengths at which we are not measuring anything, because everything is absorbing there. If we measure at 180 nanometer, everything absorbs there. Air, glass, water, and so on. It's totally useless. Except if you have vacuum, there is nothing. If there is nothing, then of course nothing absorbs. Then we can measure our sample also at 170 nanometer, which is great because I said everything absorbs at 170 nanometer. That means basically we can measure everything. We can measure everything with a UV meter if there's vacuum around. And of course it has to be gas chromatography, because if you have a liquid, all that liquid would also absorb our UV light, right? So wouldn't work. Very new instrument, very expensive. You have a near vacuum and you measure at a very long distance, so from 100 nanometer to thousands of nanometers. And it works the same way as a basic UV meter. You have a radiation source, that means a lamp, you have a sample, and you measure how much light is missing. That's it. The only thing is you do that from 100 nanometer, not from 200 or 250 nanometer. As I said, universal and also quite sensitive. So it's a very good detector, but as I said, new and really expensive.